have a seat?
Me here,
Oh,
right?
you're over here.
Oh, okay.
Either, I guess. As the guest, you should be able to sit wherever you like. So, would you like some coffee?
Oh, yes.
Part of our
certainly.
tradition here.
My life consists of coffee, yes.
So, let's start at the beginning. Where were you born?
I was born in Poland, actually, what is nowadays Poland, and belonged, to Germany before World War II was over, And so my family is very German, and it is a boundary area, between Poland and Germany throughout centuries. And of course, people mixed in this area. So my father's name is very Polish, and my mother's name is very German.
Well, I was going to say that Christian doesn't sound like a very Polish name.
No. That was actually because, you have to see, I was born after World War II. The Germans had just killed a few million Polish people, so the Polish were not really, in favor of the Germans. And there were actually pretty strict rules in terms of what you could, how you could name your children. And it had to be Polish names, or they had to be Christian names, because the Catholic Church is actually very strong in Poland. And so for that reason, my mother picked, basically very Catholic names, to get around it,
And what did your parents do?
Oh, my mom was a secretary at a university in Germany, and my father was a truck driver.
So was there science in the house when you were growing up?
No.
No.
I don't know.
Your family got permission to move from Poland to East Germany at one point, but you didn't stay in East Germany.
Yeah.
Now, the Berlin Wall changed your life twice. Once before it went up, and once after it came down.
Yeah.
Can you tell us about what happened with your family before the wall went up?
Yeah, it is. Life was tough there in a country, where there was a little bit of, let's say, payback time, And my parents, for example, couldn't speak German language there, and it was a crime in essence. And so my mother kind of pushed very much that we would come to Western Germany, but that sounds bad.
I don't think that's somebody's beatboxing, it's not me.
Maybe it's my own, maybe I just put that. And so actually, they moved away there for that reason, because they felt, that they couldn't live with their German culture. And so it was not quite an easy thing, because it was called, you left the republic, you were a traitor basically, and so you had to go across different countries, like for example from Poland first to Eastern Germany, and then in a night and train action type of thing, from East Germany from East Berlin actually to West Berlin, and there were really strict controls, on these trains, and so whenever you got caught, you actually ended up in jail, and so my aunt had actually ended up in jail, for Republic flight, and so that was 2 years before the wall came up, And they built the wall for that reason, to stop actually all the guys, going from east to west.
And even after you ended up in West Berlin, your brother Lucian told me that he went to 8 schools in 1 year, just because you were moving so much to different refugee camps.
Exactly,
over the course
exactly.
Of the
Basically, he was just his first year in school, so wherever you went, he needed to go to a new school, and I was just preschooler, so it didn't hit me that much, but he saw a lot of schools in the first year of school. Yes, definitely.
And you are the middle of 3 boys, and I
Right.
think we have some pictures of you in your youth. There we go. And what did I do with the point? And there you are on the left in both pictures. Is that correct?
Yes.
Yeah.
Yes.
Excellent. So what's the best and the worst thing about being a middle child?
The best and the worst. The best is probably, that all the responsibilities go to the older brother, because he needs to look for the younger children and things like that. The worst probably is, that the biggest attention goes to the youngest. And so actually, as a middle child, you slip through everything. No responsibility and no attention,
Okay.
Something like that.
So your brother, Lucian again, who I talked to, in response to the request, finish this sentence. Christian Kisielowski is, he said the following: Christian Kisielowski is a very talented scientist and a very nice guy. I like him very much. Every time we meet, we have a good time. Every time I've visited him, it's been a party. A party? I'm wondering if you'd like to elaborate on that at all.
Well, actually, yeah, there's a lot of traffic since he flies flew for an airline, and so we meet each other quite a bit. And he just loves to drink some German beer, and
so he's the party animal. He's not here.
That, or some wine, you know. And so yes, we usually kind of take the opportunity and go out and have a good time. Yes.
Okay. Well, we'll be looking for you down at the bars. So you have 3 children.
Yep.
13, 25, and 27. Actually, your son is here along with your wife. Wave to everybody so they can see you. There they are. This is family. But none of your children carry your name. Why is that?
Yeah, that was something, I have a very strong sense of, to be just and things like that. The point is, that if you look at the different cultures, usually females are expected to take the name of their husband, when they marry, and I think this is actually quite unfair, and so whenever I married, and I'm married twice, we actually drew straws what the family name was, and I lost twice, so that's why all the names of my children are different,
That's fair. What were you like in high school? What were you good at? What did you like to do?
Actually, I was much slimmer, as you can see there. I did actually gymnastics a lot. I liked sports a lot. I'm very strong in mathematics and all the natural sciences, and perhaps not that strong in languages, So I always made alliances with those people who are good in language but could have some help in mathematics, and that gets you very well through high school. There's no problem then. So yeah.
Right. And then later on, you were a lieutenant in the German army.
Yeah.
What did you learn about yourself in the military?
This was a little bit like in this country, that you have a lot of opportunities if you go to the army, and they provide you with finances and all these things. And I actually wanted to stay there first for a longer period of time, but then you have to have a certain character if you want to survive this army thing. You kind of there's some kind of strict obedience required, without much thinking, and I felt this doesn't really fit my character, and so after 2 years I basically said, okay, that's all very nice what you're doing, but maybe I go in a direction where I can have more freedom in what I think and what I mean, and so that's why I left. Yeah.
Okay. And what was your first academic interest?
Actually, in the German army, I wanted to learn about flying, build some, let's say, spaceships or something like that. And then I loved the sea. Mm-hmm. And so I had this possibility to go to university and study oceanography. And there are 2 places in Germany. One is directly on the seaside in Kiel, and the other one is more inland, which is Cologne. And the difference is, of course, that one has the ocean across the door, and the other one doesn't. But the other difference was, in the one town there was my girlfriend, in the other one there wasn't. So I, of course, preferred the girlfriend solution.
So you get to Cologne. How long does it take you to notice there's no ocean there?
I think even the university took something like 3 or 4 semesters, and then they realized there's no ocean there, and they stopped this branch of study. So I was not the only one who kind of didn't realize that there is no ocean. So yeah, about 3-4 semesters.
She must have been pretty, that girlfriend of yours. Yes. Your daughter Neela said that you have to be near the sea.
Yeah.
that she can't imagine you living any place where you're not near the ocean.
Yes.
And she has great stories about you taking summer vacations together and going on great adventures. She told a story about you guys ending up getting a little disoriented on a mountain hike and hiking for 14 hours to find your way back and meeting bears and all these great things. But we actually were able to find footage of a holiday that you took with your daughter where you spent time in the ocean with a few friends. Let's take a look. I believe that's your daughter.
Yes.
So, am I correct in assuming that that's your idea of a good time?
Yeah.
Okay.
I mean, if you are microscopy, you need to get training, you know, for the real life, and microscopists are like shark, you know. So it's
so
quite appropriate, you know.
Okay. Now, when you were at the University of Cologne, there was a guy named Alexander.
Yeah.
Who was a bit of a mentor to you.
Yes.
What did he teach you that stayed with you all these years?
There's this issue, you know, that if you make science, you know, and you are usually very dedicated and you pursue a particular goal, but most people have actually or many, let's say, you know, have no control about how well the science is that you actually do. And he was always very, very thorough in looking, you know, when you have achieved something, please look back first before you kind of announce very loudly that this is something which is new and revolutionary. And so I think the thoroughness in terms of and carefulness in science, you know, that is something certainly which he kind of promoted a lot.
Now, how did you get from oceanography to physics?
Oh, that was just simply counting. You know, I had this several semesters of oceanography behind me, and then the ocean was not there, and so the university stopped basically, you know, all the studies there, and then I needed to look, you know, where did you have your most certificates, and it was in physics, and so I continued with physics.
Did you ever regret not sticking with oceanography?
No, not at all. It's kind of, you know, I think physics is quite exciting stuff, you know, that you can do. And you can go shark diving anyway.
So we're going to fast forward a few years. You have your PhD and your teaching certificates in physics.
Yeah.
And we mentioned earlier that the Berlin Wall changed your life twice.
Yes.
How did it change your life the second time?
Well, the German system is actually very different from many other systems in the world. So you make your master's, you make your PhD, and then if you want to get something like the possibility to teach at the German university, you actually have to pass a second thesis, which is actually much more demanding, you know, than the PhD thesis. So it's something like an assistant professorship here or whatever, you know. And so I passed that one, and then I thought maybe I can get you know, a good professorship in Germany. But that was exactly the time when the world came down. You know, this was actually 1989-90 when I finished there. And that was a very, very bad timing for finishing your studies, because the government basically froze all support for science, because lots of these things had to go to the Eastern country. And there were a lot of people who kind of just were hanging in there, you know. And so you hang in for half a year, you hang in for another year, and then you start thinking, if I continue doing that, I might be dead in the water. Mm-hmm. And a friend of mine bumped into me at one conference and confirmed this opinion and said, basically, Christian, if you continue doing that, you will be soon dead. So why don't you come to Bell Laboratories? And that's where I left, you know.
Okay. And this was Abbas Ormaz?
That was Abbas Ormaz, yeah.
And so you went to Bell Labs?
Yeah.
How long were you there?
3 years.
And why did you leave?
Because, you know, that was the time when they decided to make all the small companies from Bell Laboratories, so a lot of people left there. It was just political issues, you know, that shareholders wanted to have more money, so they split up the company, and they kind of made many small companies out of that. Mm. And it's very sad if you nowadays go to Murray Hill or to Homedale, you know, it's basically empty halls, you know. So it's everybody left in essence.
And both you and your wife are physicists.
Yeah.
So when you knew you were leaving Bell Labs, you decided that you wanted to go someplace where you both could work.
Exactly.
And that's how you ended up here at Berkeley. You both.
Yes. Which punishment, you know, is that?
You got to UC Berkeley. You started at NSEM in 1997.
Yeah.
How did you get from UC Berkeley to NSEM?
Actually, Damen called me up. You know, I was just working on MBE growth of gallium nitride thin films, and got a telephone call, and Uli said, you know, we have this opening here at the NCM, and so I interviewed with him and got the position. Yeah.
That sounds pretty good.
Yeah, I had rarely applied for a job actually. I was
sounds
very
like.
lucky. You know.
So again, according to your brother, when you want something, you get very focused.
Oh yeah.
And you just focus on that one thing, and you don't let go. Everything else around it is you let all that go, but you don't let go of this thing until you figured it out. And your daughter says something very similar about you, that you have to find things out. You need to know how things work.
Yes.
And you'll focus on it until you know how it works, and then and only then can you let it go. Do you recognize this characteristic in yourself, and how do you think it has served you in your career?
I think it is very important because you see, there's so many choices that you can make as a scientist where you want to work, and of course everybody makes this choice. And if you want to make a particular field or the area where you're working known, you compete with a lot of colleagues, for example. And this is a natural process that comes with it, you know. So it's those guys, you know, who are weaker, they just sit out, you know, with time. And if you want to push for something, I think commitment and dedication is something which is very important to scientists, I think. Yeah.
So you're now at NSEM. And NSEM has a lot of cool microscopes.
Oh yeah.
You know, you have the ones I'm most aware of are the OAM, the Titan, and the Team microscope. And these three microscopes seem to very well illustrate the progress of atomic resolution microscopy. And we actually have a slide also that illustrates this. And I'm wondering if you can talk a little bit about what we are looking at here. And Jerry, can you get me a pointer? I don't know what I did with the last one. Sorry.
So what you see in the upper row of images, this is what people call mazed bicrystals. And this is something that Uli Dahmen grows since, for example, many, many years. And they are interested in boundaries. But on the other hand, you see that this is gold. And it gives a terrific contrast in an electron microscope. So no matter how bad or good a microscope it is, you stick a sample in there and you get a signal out from it. And so for many years I actually took these samples, you know, and went from microscope to microscope, stick it in, and find out, you know, how well does this particular microscope perform. And so if you go, for example, you know, to the very left side, this is the OEM. This was 10 years ago, actually, and that was the microscope where we got sub-angstrom resolution with. So later on, you know, in the last 10 years, there was suddenly a lot of talk about sub-angstrom resolution. But we do that actually since 10 years, and the OEM is actually a very, very terrific microscope. This was actually my job when I joined as NSEM, to make it work.
And that was quite advanced for its time.
That was quite advanced for its time.
Even now.
This was actually something which was very nice. You know, the lower bottom of images is something which the human brain does not usually understand very well. You know, it's the same information that you have in there. It's nothing different. It's just that in the upper part of the three images, you know, you see real space, so you see the real object, and in the lower part you see reciprocal space. You know, so if you see a picture like that, it looks very odd to us, but it's actually the same information that is contained in there. And it is much easier for a computer to understand reciprocal space than real space. So, and what you can see there's these red rings, and this is 0.8 angstrom, so that is sub-angstrom. And if you look, for example, from the left image to the central image, this central image is now taken in a microscope that was built much later than the OEM. That is a Titan. A lot of people want to buy these Titans with aberration correctors these days. I think they just sold, FEI sold 100 of them. You know, just there was a recent anniversary. Stanford just got one of these things. You know, want to have one of these things.
And how long has that been at NSEM? How long is the Titan?
We have never bought a Titan. This is actually something which I kind of we got something which is similar for experimental purposes, but we could never buy something like that because you see, such a microscope costs, let's say, $3 million. And if you go to the DOE and say, you know, the left result and the middle result, yes, in the middle it is a little bit better, you know what you see there, but it is certainly not such that this would be, you know, a big difference. So the difference between such a microscope and such a microscope is marginal. Mm-hmm. It is very little. The big jump came actually between these microscope and then suddenly the T microscope. Mm-hmm. So we had to go for something much better than was actually provided by industry. Mm-hmm. And that's why the team project came along, you know, and we improved on microscopy a lot. Mm-hmm. So it is not only that you make a Titan, this T microscope has many goodies, you know, that actually other people simply don't have.
And what does TEAM stand for?
Transmission Electron Aberration Corrected Microscope.
Okay. So setting aside the fact that I think it should actually be called the TECM, since there's a C in there. Can you talk a little bit about this aberration correction, why it's so important? I know there are two kinds of corrections. There are two types, spherical and chromatic. And I think we also have a slide on this. And maybe you can just walk us through this a little bit and tell us why these aberrations are a problem, first of all.
Yes.
What they are and why
they're.
Thank
you for having all these slides by chance.
It's almost like I'm psychic.
So probably everybody knows best is how a lens works, you know, and that's geometrical optics is something which we do in school, you know. So if you have a lens here, and if you have rays coming in, they are parallel, so they hit the surface of the lens in a particular manner. Then all the lens rays, no matter where they go through this, all the rays, no matter where they go through the lens, are actually focused into one point, and that's the point where the image would be, for example, created. Now, this is in the perfect world. If you kind of take a ruler and some pencil and draw it like this. In the real world, it is very different, and we know that. One problem is, for example, you know, if the lens has different properties at the edges than in the center, then you create a mess of focal points here. It's not longer one certain focal point. And this is very typical for every lens, no matter whether you take a camera or whether you take an electron microscope, you know. It's very difficult to design a lens such that you maintain one single focal point. And you can imagine then if you have a point that is actually imaged here, this point becomes a whole area, it becomes a disk, it blurs out. And if you have this effect, you actually lose resolution and you lose sharpness of image, you do not see that very well. This is what the eye does, for example. This is one sort of aberration. We call that spherical aberration. The other aberration that is very important is every white light that comes in can be split up into colors. And here I have done that for green and blue and red, for example. So if you now have a parallel beam coming in and it has a different wavelengths, then you actually create a whole range of focal points that depend on the color that of the light that actually comes in. And that is something which we call a chromatic aberration. You also know that very well from lenses. Very often you look at the edges and then you see suddenly rainbow colors at the edges. And if you buy a poor lens, it's easily visible. And so both of these effects actually kind of blur the image, make things less visible, and give you simply bad vision.
Mm-hmm. Yeah. So I think we also have examples of corrected and non-corrected things. Yeah. So one's from the Hubble telescope, which is a very famous example.
Yes.
They sent this expensive telescope into space, and then, oops, it's nearsighted.
Yes.
So
this is how they looked, you know. They shuttle up, and then suddenly, you know, you get this bad image back. It's a bad reputation.
Yeah. And then an image closer to home, perhaps from the team 0.5.
So actually, they kind of needed to send a second shuttle up, you know, to repair that, to exactly correct for the lens aberrations. And then you got glasses on the Hubble telescope, and then you see much better, And this is exactly the same effect. This is actually a picture that was taken again from these gold films very, very many years ago from Penisson, when the 1 million volt microscope still was in one of these silos. And it shows actually the same material. And you can see here, for example, how fuzzy all the atomic columns are. And here how sharp they become. And this is exactly the same effect, and that's because of the aberration correction that comes in there. Yeah.
So here are some statistics I found on the TEAM microscope. It's the world's most powerful microscope. It has a power cable as thick as a fire hose.
Yes.
And it can view objects twice as small as the last generation of the world's most powerful microscope.
Yes.
Now, these are just stats for the TEAM 0.5. You now have TEAM 1.0, which is the next generation. What's the fundamental difference between TEAM 0.5 and 1.0?
Yeah. The TEAM 0.5 corrects only for the spherical aberration, but not for the chromatic aberration. And TEAM 1 corrects for both the spherical and chromatic aberrations. Plus, there is other gadgets that get on it. For example, today we worked with Peter Dennis on the new camera system that goes into TEAM 1. You have to imagine electrons were always first detected on film, and then people came up with these CCD cameras that are actually made for optics. They are cameras that are built for detecting light, but not electrons. And that's a very bad solution actually for electrons. People used it because it was available and it was convenient, but actually the cameras that we use for detecting electrons are very, very poor. So LBNL, Peter Dennis and all the engineering guys, they came up now with a direct electron counter. And we just did today experiments with this new camera, and it is gorgeous. So it kind of allows you now to detect things even much faster than we did in the past, and it kind of gives you much better signal-to-noise ratio. So there will be another boost just simply coming through the fact, that you actually harvest more signal in a better way. Another thing that goes in the same category is the stage development is ongoing, that you with time will have a better stage, that you can turn in the microscope and go three-dimensional electron microscopy, for example. Yeah.
Oh, wow. So TEAM 0.5 was named because you wanted to see materials at 0.5 angstroms.
That's what people think.
That's what people think. That's not true.
It's half the team. You could also say it's half the team.
I was going to say the TEAM 1.0 actually you can see smaller things, but it has a larger number, which confused me. It seems like the next generation should be TEAM 0.25.
This is actually a big question that is arising, because you see electrons, when they go through materials, there's a physical process involved, which is scattering. It's Coulomb scattering. And the resolution that we get is now so fine, so good, that actually we can improve the resolution, but the blob in an image for an atom or for an atomic column will not improve anymore. It's now the physical size of the scattering process that actually limits, the size of the object or the size of the atom in the picture, and not longer the microscope. So you can push for resolution, sure, you could do that, but you would not gain anything because there's no material on Earth where you can actually exploit it. But what you gain with these microscopes is much better signal-to-noise ratios. So, for example, with these microscopes, we see now every single atom across the periodic table of elements. You can look at carbon atoms, you can look at germanium atoms, you can look at gold atoms, and you can see all single of them, And that was absolutely not possible before. And with these new gadgets that we have, we will just improve the detection of the detection limit of such atoms. And that's very important, because sometimes you have to be fast. And sometimes, there are materials around that cannot stand in large dose, for example, and then you want to have the minimum amount of electrons that you use for imaging, and that requires that all your system needs to be at a very, very high edge to not lose signals that's unnecessary. So it's a noise that actually kills us at this point, and not longer the resolution.
And how many team microscopes are there up and running in the world right now?
There's up and running. These are at the moment the only two. There's our biggest competitor is probably McMaster's University, where they built a similar thing like TEAM. It's just that they don't have the imaging capabilities for TEM. There are different modes that you can kind of operate this microscope in. So they specialized in a mode which we call scanning transmission electron microscopy, and that is probably within the next few months, up and operational. So it will kind of compete on the spectroscopy and STEM mode with TEAM. Mm-hmm. It has become almost a matter of national pride, mm-hmm. that every country wants to have one of these TEAM microscopes. So in Japan they have a development like that. Germany bought already two instruments like that. Belgium bought one. You have to imagine it's a huge effort for all these researchers in this country. For example, the people that buy it in Belgium, they're a good friend of mine, but they had to raise half of the annual budget for science to actually buy such a microscope. And then they managed to get this. That is quite an effort for them. So I'm actually traveling quite a bit around, supporting, people in their, if they strive, to actually get such microscopes in, because I don't think it is a good thing that it is always good to be the first, but if you want to grow a field, there must be many of them around in the world.
So would you say the TEAM microscope is somewhat of a celebrity?
Yeah, definitely.
So I guess it's safe to say then that the TEAM microscope is sort of like George Clooney.
Oh.
Perhaps we have George Clooney here at LBNL, that's all I'm saying. So when you manage a celebrity as big as the TEAM microscope, I imagine that a lot of people want a piece of the microscope. Everybody, and NSEM is a user facility.
Yes.
Now, do users get a chance to use the TEAM microscope, or is it like there's three guys that have a key to the secret closet? They're not going to tell anybody.
It's certainly not that, In fact, there's a very efficient system in place how it is regulated that people can access the NCM. And I think it is by now the same system that is in the molecular foundry, that is in the advanced light source. So it goes through a proposal process. These are external reviewers that actually kind of look at the proposal and say, look, this is good science, this is bad science, this is something we want. And I'm very grateful for their work, because if you wouldn't have these people in place, you would exactly have the situation that some people will come up and say, look, you have this friend in this corner, and therefore you can access TEAM, We don't want that. We really want to make the microscope available to a large group of people, and it should be a fair process, and there's all these instruments in place that take care of it, yes.
And the TEAM project actually brought together 5 leading microscopy groups supported by DOE Office of Science.
Yes.
And I think we have a map that shows the location of these. And I'm guessing that each institution played a unique role in the TEAM process here. What did the National Center for Electron Microscopy contribute? What was our role?
First of all, you have to imagine, as always in science, it is a very diverse community. And that it happens that you could combine such a large group of microscopists, that by itself is unique. That was never done before. So that you kind of actually get all these people together and pull on the same string. That was, huge amount of work. And finally, everybody agreed on that. And so LBNL is actually the lead laboratory in the whole TEAM project. That's why we have the TEAM 1 microscope here. So this is the final product, and this went to LBNL. Argonne has, for example, the first CCCS corrector. So they did actually the CCCS corrector in development. We have now the final program from this product from this development. Oak Ridge National Laboratory did the probe type of microscopy, the scanning transmission electron microscopy with the aberration correction that went on that. And that was developed in Oak Ridge. Urbana did together with LBNL the stage development that was in there. And then there are these two companies in Europe. So FEI is actually the microscopy provider. It has a big factory in Eindhoven in Holland, where the Electron Optics is located. However, it's an American company. It's located in Hillsborough. And the aberration correctors are actually built in Heidelberg by Sears company. So they have all the knowledge, how to make these glasses for electron microscopes. And this is very, very detailed knowledge that goes in there, And you have to imagine such an aberration corrector is a piece of equipment. It's not like the glasses that we have on the nose. It is it weighs half a ton. It has 150 power supplies, and it is entirely computer controlled. Mm-hmm. Some of these power supplies, they need to meet standards in terms of stabilities that are actually not defined by the National Institute of Standards. And so we actually they actually kind of build electron microscopes and see the deflection of the electron beam to actually find out, whether the power supplies are stable enough. So new ways of measuring, stability of power supplies were involved. Hmm. So this is very demanding technology.
And we have a picture of the team microscope. There it is. And it lives in its own special room.
Yes.
And the room is unique.
Yes.
Can you tell us about the team room?
Yes. So if you just looked out of the window, you have seen these two silos there. That's were the place where the two high voltage microscopes were actually living in the NCM. That were the microscopes around which the NCM was actually founded. And this was older technology, so we removed them, and we had these two empty silos. And first of all, you have to see that to make something swing in half a size of an atom, that's very easy. If I just talk in the room, for example, and my sound waves would hit, let's say, the camera there, the shaking of the camera is much more than half an angstrom. So you have to isolate it from the ground. And there are very good isolations in this two silos because there were these big microscopes standing. Then you have you need to make sure that there is no additional sound waves being built up in that room. So we built a house in the silo, and this house, the walls from that house you actually can see here. They are all at odd angles, so that you can actually not build up standing waves. It's very low magnetic fields in there. The temperature is controlled through these panels here, and what is allowed, for example, in the Team 1 room is a temperature fluctuation of 0.1 degree. And so it needs to be very stable in temperature, otherwise, the performance of this microscope changes. So the rooms take care basically for ground vibrations. Electromagnetic fields need to be staying out, and these are good sites for that. And you need to control the temperature very well. And that's why you need to have these rooms.
So is that a short person or a very tall microscope?
This Marta, that's Petra size, I would say.
Okay, so how tall is the microscope?
I think this TIMO 0.5. This is TIMO 0.5. This is a smaller one. That's around 4 meters, and the Team 1 is a little bit higher. It's something like 4.5 meters tall.
So Team, as we've been talking about, has allowed you to see things that you could not see before.
Yeah.
And soft material has been a problem for a long time for imaging guys. Exactly. And I'm wondering first if you could just tell everybody what soft material is, and second of all, why it is such a problem to image.
Okay. So for many years, material science, looked at the things that society needed. For example, if you want to improve on airplanes, you need to look at aluminum. You need to make aluminum hard, for example. If you would take a jumbo jet, and build them, everybody knows jumbos are built from aluminum, but if you would build it from aluminum and roll it out on the runway, the material would be so soft that the wings just would lie on the ground. You could not even fly a jumbo, it would smush under its own weight. So it is actually the design of the material, that actually kind of allows you to make the material very hard. So people kind of looked at it, for example, in metal physics for bridges, in semiconductor physics, you know, to build all this small semiconductor chip. Now, over the last years, I would say 5, 10 years, for example, people also found that there is much better materials around, you know, that there are new materials around. Many of them are composites, you know, where you actually see that you can make a mixture of for example, a metal alloy together with what we call soft material, and then you get properties that are suddenly much better than what you had before. You know, there's a big debate in the aviation industry, for example, whether the next hulls of airplanes should be built from composites instead of metals, for example. Mm-hmm. And they can be very, very strong. And so, what is then the difference between these hard and the soft materials? It's actually the arrangement of the atoms. Mm-hmm. If you look at a hard material, in a traditional hard material, if you put together two atoms, they like to go in particular positions. They create beautiful patterns. You know, they kind of arrange in certain symmetries, and they go all exactly to the same place. Mm-hmm. Now, the first thing that goes away from that kind of arrangement of atoms would be a glass, where the atoms are quite disordered. Mm-hmm. And now if you combine this disordered type of atom arrangement with atoms, you know, that you find in nature, for example, you know, you use hydrocarbons, for example, for that, you know, you get totally different properties again, and you get materials, you know, that are just, if you touch them, much softer, for example, you know. And so these soft materials are nature-inspired polymers, for example, which last, you know, artificially in the molecular foundry, for example. And the great interest and the excitement about soft materials comes about because you can kind of combine these materials with hard materials, and suddenly you gain properties that mankind was not able to do before.
What's the challenge in imaging, say, hydrocarbon?
Yeah, so if you now look at a hydrocarbon, you know, and let's say you have a carbon atom here and you put a hydrogen on it. Mm-hmm. Just think about the electron beam that comes down in this particular column. And this is a small atomic bomb, you know, that actually hits the sample. I mean, we get something like a current density of several hundred amps per square centimeter that actually kind of pull down the current. So if the electrons, and they are at a very high energy, you know, they are 300,000 volts, you know, 100 amps coming down on the sample, they hit the atoms, and of course they break bonds. Mm-hmm. Now, if you look at hydrocarbons, for example, there's this hydrogen atom here, and it's a proton, and it has only one bond. You hit that, and the hydrogen has nothing to hold on. You know, it just flies away. So to actually image hydrogen atom is very, very challenging. It goes out very fast because it is not very strongly bonded to into the material, and the electron beam hurts it a lot. Mm-hmm. And so that's why it is much easier, you know, to look at images like from let's say metals or semiconductors than to look at images from polymers.
But you and Ron Zuckerman, in alliance with the team Microscope,
yes,
were able to get a beautiful image of strings of hydrocarbon.
Yes.
And if you could just tell us what we're looking at here and why it's important.
So maybe we come later on to these images, you know, where you have a nice pattern, you know, as it is in hard materials. But in fact, you know, I think actually they are much more boring than this one, in spite of the fact, you know, that this image it looks like a mess. You know, when you see something like this, there's no order in there. You don't hardly know what actually these things are that you're seeing there. And if you look more carefully, like for example, I've blown up this area here. So this area is this area. Mm-hmm. So we certainly have altered the material because of the electron beam, but what you still see is the strings of atoms. All the balls that you see in here is actually, these are all carbon atoms. And so for the first time, we were actually able to get an image, may it be altered because of the radiation damage or not, of polymers. And this is a first in mankind's history. And so I was really, really excited, you know, about seeing an image like that, because you see, Ron has this huge chemical machinery, you know, in the molecular foundry, which I do not understand at all, you know. but he can kind of alter all the bonds and the constituents of these things very, very much to his liking. And if you, for example, have now a problem with losing hydrocarbons or hydrogen out of these things, you can even put other atoms in there that would be more stable. Mm-hmm. So our problem here was, for the first time, to keep this polymers actually in its place for a time long enough to make an image. Mm-hmm. So that is solved in this picture. Now we can go ahead and basically see how much we can alter the chemistry in these chains and see, what can be done with it. And this is very exciting. That was not possible before, simply.
I think we also have an example of some ordered, more periodic. Oops, maybe we won't see. Oh, there. Very.
Yeah,
the Swiss in me likes this very much. So that's just a difference between periodic and aperiodic.
Exactly.
Right? This is periodic, and what we were looking at before, the disordered.
Yeah, this is a hard material. The other one is a soft material, yes. Okay. And this part particular is, this was very important for us, because you see, people usually, if they do these images, it is not a single atom that you see here. Instead, it is a whole column of atoms, because in every imaging process, you actually shine the electron beam onto a sample, and the sample is a three-dimensional object. And then you kind of make a projection of all the three dimensions into a two-dimensional image plane, so you lose the third dimension, basically. So if people look at lattice images, they basically find in each of these points, atomic columns. They have a finite thickness. Now, graphene came very, very handy at that point, because we know it's actually just a single layer of carbon atoms. And that means that each blob in this image is actually a single carbon atom. There's no doubt about that. And so what this image shows them basically is that the sensitivity and the performance of this microscope is so great that you actually can get single carbon atoms very well imaged. And that is something which kind of excited a lot of people, and we got Science magazine out there, nano letters and title pages, and this is research with Alex Zettel, And this is actually basically when we saw this, we thought, maybe we give it a shot to the soft materials, because there are also carbon atoms in there. They might be just disordered, but we should be able to image them, and therefore we kind of went for the peptoids, with Ron.
Yay, peptoids. And you mentioned how when you take a picture of something, you're taking something that's three-dimensional and making it two-dimensional.
Yeah.
But the team microscope is really moving you toward being able to get that three-dimensional structure back.
Yes.
And we also have a slide that shows this. This is a pretty cool slide. And again, if you could just tell us what we're looking at.
Yeah. So in essence, you see, if you get now a microscope, and this microscope is able to see every atom in the periodic system of elements. So the automatic question becomes then, maybe we just take a sample and we rotate it in space and look from different orientations, and we image all the atoms from different angles, and then we get this three-dimensional representation of this material. And we do that every day, or maybe not every day, every one of us, but if you go to the doctors and you get a CAT scan or you get an MRI or something like that, it's the same story. They put the patients, into a detection machine, and then they do not rotate the patient, but actually the detectors around you, and then they make a three-dimensional image of your brain or of your spine or whatever is just, the object of interest. Now, with electrons, you can do the same story. Now, the difference is just that if you have this ability to see single atoms, it's quite interesting to think about that from a theoretical point of view. Oops. Now I lost this nice microphone, which is not good. Because you see, usually we are acquainted to calculate in terms of functions, for example, and they're all continuous in space. But nature is not that way. If you look at that level onto nature, it is discrete. So it is not such that you have, a function well defined here, and then you can go through space, and then you go somewhere else, and it is well defined here. There's gaps in between. The gray levels between the black dots there's nothing, right? There's vacuum. So we actually thought, that a much more adequate description of nature on that scale is actually discrete. So I have these friends who are mathematicians, in discrete tomography, and we actually thought maybe we use the atomicity of nature to come to a much more adequate description of what you can do with these microscopes. And this is a first example for that. This is actually something which is a germanium crystal. So these two things, these are two atom columns of germanium, and then we irradiate it with the electron beam, and then you can see all sorts of things happening. For example, you see here you have these two atom columns, and this one swings. It swings around this point. And then you see the trail here, and so actually it spits out an atom. And now we can go ahead and actually say, okay, from the gray value that you measure here, we can actually count how many atoms are in this particular column of atoms. And you can calculate these things, and then you just say, oh, it's 1, 2, 3, 4, 5, 6, 7 atoms or whatever, put then the data points on top of it, and then you can say in this particular column, you have actually 5 atomic columns. So this is a plan view, so that's how we look in the microscope onto the sample. This particular image is now a side view. So we actually kind of reconstructed, the thickness of the material through knowledge of how the contrast would look like. And since atoms are discrete objects, it is not a continuous function, it's just, a stepped function that goes across these things. And then you can go ahead and say, look, I know how many atoms are in each column. So these are the green balls. And then I look at an interstitial, for example, and germanium interstitials were never imaged before because people couldn't do that as simple like that, right? And then you know the contrast of these things, and then you say, okay, now I know that the interstitial is actually sitting here where the blue cigar is, having the biggest blue, and these are just the errors of the measurement. We did that then twice. So actually we have one projection, and from one projection we actually recover the three-dimensional structure of these materials. What we want to do now is actually look at 2 or 3 projections, and you could do that with every material. So you would see for every material what its three-dimensional structure is on the atomic level, and you only need 2 or 3 projections. And the reason for only having these 2 or 3 projections is actually that nature is discrete on this level. Atoms are discrete things. That's a very powerful constraint.
So there are really 2 things going on on this slide. One is the atom moving.
Yes.
Right? And the other one is creating a 3-dimensional image. And these 2 things were not possible before the team microscope. Is that correct?
Correct.
So this is really moving forward.
This is really moving because you see this gray stuff in here, this is vacuum. And since the resolution of the microscope is so high, the atom columns, these black blobs are so narrow. In usual microscopes, this would be really, really black blobs, and you wouldn't even see the vacuum in between. And so the high resolution allows you actually now look into the interstitial sites, and the high sensitivity allows you to look at single atoms. And then you can utilize, atomicity and actually go into the 3rd dimension.
Wow, that's pretty cool. So we've come to the end of our conversation. I know there's a lot more to talk about. There are a lot of things that we didn't get to, so maybe you'll come back and we can talk about green technologies and Helios and all these other things that you're involved with as well. Your brother said about you, quote, that my brother is very easy to handle because he's not a troublemaker. He knows what to do and he takes things as they are. So I'd just like to say in front of all these people here, I would love to be your manager. That sounds like one. Sounds like a pretty easy 15% to me. And your daughter said about you, I'm really proud of my dad. He taught me that no matter where you start, if you really want something and work for it, it will happen. I admire him. He's had to make difficult decisions in his life, things that were really hard, but he's happy and successful. Now, we had a week and a half to prepare for this conversation, and we had the MSD retreat stuck in between that, but you have been nothing but gracious and kind and just full of humor, and I really I appreciate it, and this conversation has been a delight. So thank you very much for being here. And if there are any questions from the audience, Dr. Kisielowski, here's your audience.
Okay, so anytime, thanks a lot, I did. So, if there are open questions, I'm more than happy to ask.
We saw a lot of great things.
Yeah?
I have two, actually. First of all, going back to the image of the polymers or polymers.
Yes. These are peptoids,
Peptoids.
as I learned from Ron.
Oh, thank you. Are those enlargements that you provided there, are those provided by the microscope itself, or are those provided by your manipulation of the image afterwards?
Oh, this is actually the image as you record them.
Right.
And so this is just a blow up of this particular.
Okay, so that was done after the fact.
Yeah.
Okay.
You just grab a part
Right.
of that image,
With Photoshop.
and make it larger. This is
Right.
Photoshop. To record that image is actually, the microscope.
The hardware, right.
The hardware. And actually, to be exact, it's actually not even only one image, it's actually 10 images that are in there.
Use a statistical averaging, or?
And it's a different reason for that, maybe you know that if you look at an image, you look usually at intensities.
Right.
And if you record intensities, there is a relation between the intensity and the actually scattered wave. It's actually the intensity is proportional to the square of the wave.
Okay.
And as a result of that, you actually lose all phase information. Every imaging system has that problem. No matter whether you go to the light source, whether you do optical micrographs or whatever, there are huge workshops out there about the phase problem, how to solve it, because the phases are the atom position. Now, this process that we use here is actually solving the phase problem. This is actually the phase of the waves that we calculated backwards from the intensity spectrum. So these are actually very, very heavy mathematics involved, to actually kind of create that image. Yes, we see also in the single images where the atom positions are, just information, if you want to quantify the information, it's much better to have a wave.
Right.
Because, for example, in intensity, you kind of cannot propagate. You can, for example, sit at the microscope, and you can, optical microscope, we can measure sample thickness by changing focus.
Right.
We do the same in the computer, but you must have the wave, because then you can propagate the wave, right? And the propagation distance that we use here is 1 angstrom. So actually we go and measure thicknesses, of samples now at the rate of 1 angstrom. And it is because we can propagate waves. And we calculate it from the intensity of the wave.
Thank you.
How many proposals do you do each year?
That's a large number, It's we have about 200 user groups each year at the NCM. And personally, I have something like typically 60 user groups per year coming through there, and they come from all over the world. They come US, Berkeley, Europe, China, Japan, from all over the world.
What percent is where they send a sample in versus actually physically meet?
Or we actually have regulations in place to exactly prevent that. Because if people kind of would go ahead and just mail samples to you, you would be amazed what is mailed. So people come with a whole handful of material and say, oh, just give me this beautiful image of graphene from that. And it is nothing but crap, in essence. Just try to prepare a sample on a level where it is atomically flat. I mean, there's hardly any preparation tool around, that could do that nowadays. Just with the Helios project, we just bought one of these low voltage ion builds to actually help on that, exactly that point. The biggest problem with this microscope is no sample preparation. How do you make a sample that is atomically flat? It's absolutely not easy. Absolutely not. And so if you would allow for, people just mailing in samples, you will get all the crap and have to mail it back and with nothing but a bad reputation, because it wouldn't work. So we actually asked people specifically to show us images that they have recorded before from their samples for that reason.
Yeah, when you're trying to image these atoms, aren't they moving around? How do you count?
Yes, yes. There is actually, a very nice movie in this type of picture in science. This is about motion of atoms at the edge of Berkeley, for example. It turns out, that actually at 80 kilovolts, it is voltage that should not displace any carbon atoms with graphene, for example. But the thing is that very often you do not have a bulk material only.